Hello everybody. So what we're going to be looking at today is concavity and the second derivative test. So I think what I want to do before we do any math is talk about what concavity is. So basically it has to do with the shape of the graph. So concavity is basically curvature of the graph. So there's this kind of shape, and there's this kind of shape. And so the first one is what we call concave up. And the second one is what we call concave down. All right? And that's concavity, concave up, concave down. Now, if there's no curvature at all, the straight line, then there would just be no concavity. All right, and there could be a slope, right? I'm not trying to draw that horizontal. The slope doesn't matter. It's whether or not it's curved. Yeah, so that's basically what concavity is. Okay, now I guess one thing I do want to do, I guess we can do it right now, just from the shape, is also look at a graph like this. So if I have a graph that does this, and then does this, then, well, I want to draw a better one. Sorry. Let me think about how to do this. So let's go like this, and then go like that. Okay. So if you take a look at this piece of the graph here, and again, slope doesn't matter, but around here, this section of the graph, the top section here, it looks concave up. In a better color. Right? It looks like part of the concave up graph. And then down here, it looks concave down. It looks like part of the concave down graph. Okay? And if it goes from concave up to concave down, then there must be some point in there where it switches over from being concave up to concave down. Now it's pretty hard to tell where that is, exactly where that is. But you know, it's definitely concave up here, and it's definitely concave down over here, and somewhere in here there's an exact point where it switches. So if I get that dot in the exact right place, then to the left of the dot it's concave up, and to the right of the dot it's concave down. Okay? And if you do that, then that has a name. So where it switches concavity, that is called an inflection point. So an inflection point is where a curve switches concavity from up to down or down to up. It doesn't matter which way it goes as long as it goes. Okay, and that's an inflection point. So there you go. That's what you need to know. Concave up, concave down, no concavity, and there's an inflection point. Okay, now, of course, that's not going to be enough to solve any problems because they're going to ask you, where is the graph concave up? Where is the graph concave down? Where is the inflection point? So in order to do that, you need to know what an inflection point is mathematically. So the mathematics of it, or definition here, will be this. So we say, not we say, if f double prime of x is positive at a point, we say f is concave up. at that point. If f double prime of x is less than 0 at a point, f of x is concave down. At that point. And you can extend that and say, if f double prime of x is greater than 0 for every x in an interval, AB, then f of x is concave up on the interval. And similarly for concave down, I don't know if I want to write it. I guess I will. Yeah, I guess. If f double prime of x is less than 0 for every x in an interval to b, then f of x is concave down on AB. All right, so that's the mathematics. It just has to do with the sign of the second derivative. Okay, so yeah. I guess while we're at it, let's have a mathematical definition for the inflection point while we're writing all these definitions down. So think about this. What did we say an inflection point was up here? An inflection point is where a curve switches concavity from up to down or from down to up. So the concavity has to change. And the concavity is coming from the second derivative. It's just the sign of the second derivative. Positive means concave up, negative means concave down. So with that in mind, what you're looking for, if you're looking for an inflection point, is a point or an x value where on one side the second derivative is positive and on the other side the second derivative is negative. So let's write that. If let's see, if f double prime of x changes sign from plus to minus, or from minus to plus at x equals, we'll say c, then x equals c is an inflection point. Oh man, that's a new page just to say the word point. Okay, so yeah, so that's what an inflection point is. It's going to be where the second derivative changes sign. Okay, and so let's do some calculations with this a little bit. So here's an example. The homework, the first question asks me about an inflection point, which is surprising, but it's a weird first question, but we'll try it. So we have a function. Nothing special about it, it's just a function. And then they just say, what is the x value of the inflection point? I guess there must only be one. There's no rule about that, but that's what they say. What is the x value of the inflection point? Okay, so let's try it. So what is the x value of the inflection point? Well, we know an inflection point has to do with the sign of the second derivative. So we're going to need the second derivative. So let's compute, in this case, h double prime. So we have h. I don't need to rewrite it because we can see it right there. So what's h prime? So we're going to just use the power rule 3 times here. So 8x cubed, so that's going to be 24x squared. 8x squared, so that's going to be 16x. Minus 3x, that'll be minus 3. And then the minus 2 will be 0. So there's my first derivative. What are we doing with the first derivative? Nothing. So let's move on. Second derivative. So we're going to do this again. So another power rule. So we take the derivative, it's going to be 48x plus 16. That's it. That's our second derivative. Now, how are we going to find an inflection point? So if you think about this, look up here at this definition. If f double prime changes sign from plus to minus or from minus to plus, it's an inflection point. Well, isn't that exactly the same as the first derivative test? The only difference is when you're doing the first derivative test, you're using the first derivative, obviously. And for an inflection point, you're using a second derivative. So what you do is basically we make a number line for, I'll say f double prime, even though this is h, just because this is like generic instructions. So make a number line for f double prime, just like you would for f prime if we were doing the first derivative test, which we're not. If you were doing the first derivative test. All right, so let's think about that. The steps there would be like normally when you're doing the first derivative test, you have to find inflection. No, normally for doing the first derivative test, you have to find critical points. Well, there's no word that means the same thing as critical point for the second derivative. So a critical point, if you remember, is a point that might be a minimum or a maximum. It might be, but it's not necessarily a minimum or a maximum. There's no word for a point that might be an inflection point. So there's no equivalent, but we can still do the same thing. So what we're going to be doing here is we're going to set h double prime equals 0 and solve, right? Second derivative instead of the first. So 0 equals 48x plus 16. Easy enough to solve. So move the 16 over. Divide by 3. So negative 16 over 48, which is negative 1/3. Now you can kind of cheat here because the problem said, what is the x coordinate of the inflection point? And we've only got one x value. And so if there must be an inflection point, and this is the only x value that we came up with, then I guess this must be the inflection point, okay? But that's not how you're supposed to do it, right? You're supposed to verify that the second derivative actually changes sign here. So once we have that, we should make the number line. Number line showing the sign of, in this case, h double prime. Well, now I mixed up where I was saying f versus h. Oh well. All right, so you make a number line. We put x equals negative 1/3 on there. What's special about that point is that h double prime is equal to 0. Now, the reason I label it like this is because you can have problems where you have to do the sign for the first derivative and the second derivative, and you want to not mix up your stuff. So that's why I always label it that way. So at x equals negative 1/3, h double prime is 0, not h prime. So you make this number line. We know that the number line is now separated into two sections. We've got a section on the left side. We've got a section on the right side. We just do one test point per interval. So we make a number line. So we need to test points, which are x values, on each side of x equals -1/3. That's all we need to do. So that means we're going to plug a number on the left side, this side, and this side, into h double prime. So what's in the green interval to the left of -1/3? So I'm just gonna say left side. How about -1? Right, that'll work. To the left of -1/3, h double prime of -1. So you plug that into h double prime. So find h double prime. Where is that? 48x plus 16. So we got 48x, which is -1, plus 16. So what's that? -48 plus 16, so -32. So it is negative on this side. Then you check the other one. So the right side, h double prime, something to the right of -1. I mean, there's a lot of numbers over there. Let's just do 1. That would be 48 times 1 plus 16, which is 64. Well, that's positive. Like that. So it's negative on the left side, positive on the right side. So we are able to conclude that that is in fact an inflection point because the sign changes. So we can say that. I'll say it in words here. Since or because. What are we doing? Make a number line. Okay. Interpret the result. Interpret number line. What's the interpretation? We see that the sign changes. H double prime changes. Sign at x equals -1/3. So h has an inflection point at x equals -1/3. That's the interpretation. Okay, so there you go. Again, you could have cheated, stopped after you found x equals -1/3, but the number line is what proves that it's an inflection point, okay? So it's technically non-optional. All right. Let us do this. Now, they intend for us to do this a different way than I'm going to do it, but guess I'm just going to do it. So here's a question. It just says q of x, sure, why not, equals x to the 11 minus 3x to the 10 plus 2. And we want to find the x coordinate for all local maxima. Right? Okay, easy enough. Let's do it. If we get stuck, I'll teach you something new. Because this is called the, you'll notice that this section is called concavity and the second derivative test. Well, we only have the first derivative test. We don't have a second derivative test yet. So maybe they intend for us to do it with the second derivative test. I will show it to you. But the reason I'm not showing it to you right away is because I don't even always teach the second derivative test. The second derivative test is easier than the first derivative test sometimes, but it doesn't even always work. And so it's not as reliable as the first derivative test. So I say, why bother? But I will teach it to you, but I don't expect you necessarily to use it. All right, so let's do this. Find the x coordinate for all local maxima. And we'll use the first derivative test. So maximum. So what do we need? We need critical points. That means we need to find the derivative, right? So q prime, just take the derivative, 11x to the 10th minus, this is a 3, right? I can't read my own writing again. Okay. 30x to the 9th. Fair enough. There's the derivative. We're going to set it equal to 0 and solve for x. Hopefully that's not hard. 0 equals 11x to the 10th minus 30x to the 9th. So you, looks like we can factor out an x to the 9th. And we get 11x minus 30. All right. Easy enough. So we have this. Now we're setting it equal to 0. So when you have two factors like this equal 0, then you set them separately equal to 0 to solve it. So you have x to the 9th equals 0, or 11x minus 30 equals 0, and we solve them both for x. So here, x to the 9th equals 0 is just going to give us just x equals 0. The other one is going to be, well, we're going to move the 30 over, get 11x equals 30, and then we're going to divide by 11. So x is going to be 30 over 11. So I got two critical points. Critical point, critical point. There we go. Now there's nowhere where the derivative is undefined, so I'm not going to worry about that. I'm going to move on to my number line now. So we're going to do the number line for the first derivative test. How do we do it? Well, think about it. It's exactly what we did up here, except instead of the second derivative, we are using the first derivative because we're doing the first derivative test. So that's easy. We just make a number line. We put our critical points on the number line. Like so. There are now three intervals. I should label this, right? Q prime equals 0. Q prime equals 0. Three intervals to worry about. This one. This one. This one. Three intervals. So let's find the sign in each interval. So we need one test point to the left of 0. So how about -1? That's to the left of 0. So these are our test points. They usually call them that. So Q prime -1. So where's Q prime? I mean, there's a Q prime is this, but it's also this. So you just pick whichever one, whichever form looks nicer to you. I think I'm going to use the second one. I like the factored form, even though it doesn't say Q prime next to it. So -1 to the 9th, 11 times -1 minus 30. The reason I like this is I can see -1 to the 9th is -1, and then I've got -11 minus 30 is -41. And so I can see that that's positive real easy without having to grab a calculator or something. It's positive. Positive. All right. I'm going to write that a little nicer though. Okay. Now we need the middle interval. So between x equals 0 and x equals 30 over 11. Now 30 over 11 is about 3. So +1, for example, is definitely in the green interval. So let's try Q prime of 1. That will be 1 to the 9th. And then 11 times 1 minus 30. So that's 1 times -19 or something like that, which is negative. So that's negative. Then we need the third interval. Third interval is on the other side of 30 over 11. Now again, 30 over 11 is about 3. Definitely not 4. So I'm going to go ahead and use Q prime of, 5. Let's use 5. That's in the third interval. So 5 to the 9th. 11 times -1 minus 30. So 5 to the 9th, I don't know what that is. I'll just leave it 5 to the 9th. Minus 11. Oh, whoa. Why did I put a -1 in there? That's weird. Should have been 5, right? Okay. 11 times 5 is 55. 55 minus 30 is 25. Now I can look at that and say, well, 5 to the 9th times 25, that's definitely positive. So definitely positive. So there's my number line there. And let's think about it. So remember, when the derivative is positive, the function's going up. And when the derivative is negative, the function's going down. And when the derivative is positive, the function's going up again. So which one of these is a maximum? Maximum's the top of a hill, right? So this one must be, oops. This one must be the maximum, right? Come on, why? Next. So we're going to interpret our number line. X equals 0 is the location of a local max. The end. So not so bad at all. Now, again, they didn't expect us to do that. They expected us to use the second derivative test. And so I think what I'm going to do is show you what that is, since they want you to do it. Let's see here. Local maximum. Yeah, okay, that'll work. So here's our definition of the second derivative test now. So think about what a local maximum and minimum usually look like. Usually, a local max looks like this. Right? And a local min looks like this. And so what you can probably notice is that the concavity seems to have something to do with it, right? Like this one right here is definitely concave down. And this one right here, oh, why do I always do that? Do not know. This one right here is definitely concave up right there. And that's basically the second derivative test. So I can write it this way. Second derivative test very simple. So we need a point that may or may not be a local minimum or maximum. So we'll say if f prime of c equals 0. So that means we're looking at a critical point. So if f prime of c equals 0 and f double prime of c is positive, right? So if f double prime of c is positive, it's concave up. So notice that concave up actually is a minimum, okay? So if f double prime is positive, then f has a local minimum at x equals c. And of course, the other way around is going to be your maximum. So if f prime of c equals 0 and f double prime of c is less than 0, then f has a local maximum at x equals c. And so this is the second derivative test. I'm going to make it hopefully a little more obvious. Hey, that's not what I wanted. How come I pick a color and then I do it and the color's gone? Make a box. Okay. So there's your second derivative test right there. So you'll notice that it doesn't involve a number line at all. Okay, and that's what makes it easier. But also, it doesn't work if the first derivative, like remember that the first derivative could fail to exist at a critical point, and you could still have a maximum or a minimum. But the second derivative test wouldn't help you. And in fact, this doesn't say what to do if the second derivative is 0. If the second derivative is 0, then the second derivative test didn't tell you anything. So I'll just make sure you know that. Note, if f prime of c equals 0, so you have a critical point, and f double prime of c is 0 as well, then you don't know. Then x equals c could be a maximum, a minimum, or nothing. So you don't know anything. And that's why I try to avoid the second derivative test, because sometimes it doesn't tell you anything. And if it doesn't tell you anything, then you have to go and do the first derivative test anyway. So if you have to do the first derivative test, you might as well have started with the first derivative test, in my opinion. Okay, well, let's go ahead and do it. See how it goes. It is a little bit faster, I'll admit. So let's do one. Example. Find the x-coordinate of all local maxima, and just as a note, we'll use the second derivative test for this. Okay, instead of the first one. All right, what's the function? The function is g of x equals x to the 9 minus 3x to the 7 plus 2. All right, let's try it. So we need critical points. So we're still going to do that. Find all critical points. Probably not too many of them. All right, so we need g prime. G prime is 9x to the 8th minus 21x to the 6th. All right. What do we do with the derivative? We're going to set it equal to 0, like we have been, to find critical points. So 0 is 9x to the 8th minus 21x to the 6th. We got to solve this. So we are going to, what can we factor out of this? I see that we can factor out a 3 and an x to the 6th. If we factor out 3x to the 6th, we'll be left with 3x squared minus 7. What? It's insane. It's not insane. It's normal. So we set equal to 0. We need to solve this for x. So we got 0 equals 3x to the 6th, or 0 equals 3x squared minus 7. This isn't going to be that hard to solve. This one, the first one, divide both sides by 3, you get 0 equals x to the 6th. Technically, you take the 6th root here, but it's 0, so 0. So we got one critical point. Let's find some others. So we got 0 equals 3x squared minus 7. So move the 7 over. 3x squared. Divide both sides by 3. So we have 7/3. Square root. When you square root, though, you get a plus or minus. Plus or minus square root of 7/3. So there's actually 2 critical points there, plus x equals 0, for a total of 3 critical points. All right, so we got them. We got all the critical points. Now this time, we're going to do the second derivative test instead of the first. hopefully it works. If it doesn't, then we're wasting our time. So let's try a second derivative test. So for the second derivative test, you need the second derivative, obviously. So we need g double prime. All right, where's the first derivative so I can take the derivative of the derivative? Okay, there it is. Way up here. So take the derivative of that. So the derivative of 9x to the 8th is 72x to the 7th. And then the derivative of 21x to the 6th, well, I got to bring the 6 down in front. What is 6 times 21? 126, is that right? 126x to the 5th? Hope so. That should be right? Must be like 6 times 20 is 120. Sounds good. I'm gonna go with it. All right, so there you go. There's your derivative. Also, I do like oh, I don't know what numbers those have in common. We can take out next to the 5th. You don't have to at all, but I'll take out next to the 5th and have 72x squared minus 126. Just maybe that'll make it easier for us to find the sign in a minute. All right, so that's there you go. Now, what you do for the second derivative test is you do not make a number line. We plug in the critical points into the second derivative, and we're just looking for concave up or concave down. So just plug the critical points into g double prime. That's it. That's all we got to do. So we're gonna do that. So we're gonna have g double prime of what's one of the critical points? 0, right? Okay, so that is going to be 0 to the 5th, 72 times 0 minus 126, which is 0. Uh-oh. You see the problem here? I already got 0. So technically, I don't even know if this is a critical point or not. If x equals 0 is a critical point because it didn't come up plus or minus. Oh, I said critical point. We don't know if it's a local minimum or maximum. That's what I meant. Local max, not fax. Remember fax machines? Those are weird. Local max. Because the derivative was 0. All right, so that's already a bad thing that happened, right? We didn't want that g double prime to be 0, but it is. Let's go and test the others while we're doing this, though. So g double prime of, we got plus or minus root 7/3. We'll do the plus. So that is going to be root 7/3 to the 5th, 72 root 7/3 squared minus 126. Okay, awesome. Okay. So I'm just working this out on a calculator. 72 times square root 7/3 to the 2 minus 126, close parentheses, enter. 349, hopefully, point stuff. But we don't care. What we care about is that it is positive. And then we go g double prime, negative 7/3. We get parentheses negative 7/3 to the 5th, 72 root 7/3 squared minus 126. I think this must come up negative 349. I'm just looking at it, and so this is supposed to be a negative in here, right? I missed that. But like this and this are going to be the same number because you're squaring it. So the plus or the minus doesn't matter there. So the only difference in the whole thing is going to be that first term here. And this one was positive, but this one's going to be negative. Everything else is the same. So this is a negative. So it's probably going to be negative 349.29. So there we go. So this is what we got. And what I can say for sure here is that one of those is a maximum. So which one's the maximum? So we're looking for a negative second derivative for a local max. Negative second derivative means maximum on the second derivative test. So that's this one, right? So we can conclude x equals negative square root 7/3 is the location of a local max. Okay. Now, what about that 0? Well, if you wanted to know if 0 was a local maximum or a minimum, you would actually have to go do the number line in the first derivative test. I'm not going to. I'm going to cheat. I'm just going to say, well, I happen to know that this is the only one, and I'm going to stop there for this problem. So what can you see here? Hopefully you see that technically this was a little bit less work than the number line, but also it's unreliable because I don't know about 0, and that's bad. Okay, let's see what they say. Yeah, so what they do on the computer is they did make the number line. So they made the number line like this. They didn't put everything on the number line, really. I mean, I guess they did. They went negative root 7/3, positive root 7/3, 0. And so there was actually, 1 interval, 2 intervals, 3 intervals, 4 intervals, but you don't actually need all 4 intervals to work with because 0 is the only point we're actually concerned with. And so what they do is they say, okay, well, there's my number line for the first derivative test. I'm trying to write first derivative there. First derivative test. You make that number line, and then we need just these 2 intervals to check. So you can do g, and this is now the first derivative test. So g prime of something in the green interval, well, root 7/3, you can work that out on a calculator. Square root 7/3 is like 1.5. 1.5. So 1, for example, is going to be in the interval. So I can do g of negative 1. And so g prime of negative 1, I mean. So where's g prime? Somewhere. 9x to the 8th. 9x to the 8th minus 21x to the 6th. And I can see that that is positive because, oh no, I can't. I can see that that is negative because it's going to be 9 minus 21, it looks like. Negative. So this is negative. And again, this is the first derivative test here, not the second derivative. So then I can check g prime of positive 1, which is going to be 9 times 1 to the 8th minus 21 times 1 to the 6th, which is also going to be, isn't that also going to be negative? Yes, it is. Right? So, according to the first derivative test there, the 0 is nothing because the sign of the first derivative doesn't change. So we can see since the sign of g prime does not change, at x equals 0, x equals 0 is neither a maximum nor a minimum. So that's what you would have to do. Now the thing is think about it, right? I just had to test 2 of the intervals to see if 0 was a maximum or a minimum. I could just add, 2 more points to this. Like I could put like a 2 and a -2, and then I would have had the whole number line, and I would have just done the first derivative test, and I could have skipped all of this. So I could have started there and not done the second derivative test. So again, that's my opinion, but my opinion is don't waste your time doing the second derivative because it's inconclusive a lot, and then you have to do more work. Okay. So let's look at this. Let's look at graphs a little bit. There's some graphical problems on here. So I don't know how well I can draw this. Bad. It helps me draw a straight line, but there's not enough help in the world. It's really hard to draw like on a tablet, I find. See, it's really frustrating because I realized there was something wrong with my drawing and I couldn't keep it. Okay, so I'm making like a W shape. That's all I'm trying to do here. And basically what they want you to do is, well, what they want you to do I can't do on this graph, but like what it says is like use sliders to highlight an interval where f is concave down. Do not try to capture the entire range. Don't try to place the bounds exactly on inflection points. Okay, we can't do that. So what I'm going to do is I'm going to say, let's try to put dots on the inflection points. Let's mark the inflection points. And label the regions as concave up or concave down. Just to make sure we know what that looks like. All right, so remember what we're looking at. Down is like that, up is like that. Down, up, easy. All right, so what is it right here? That looks like down, right? What about here? That looks like it's still down. Oh, I said down, I mean up. Start over. This is concave up, right? Looks like a bowl shape. This is still concave up. This is still concave up. This is definitely down. So this is like definitely up, and this is definitely down. So somewhere it changes. Where does it change? Hard to get it exactly right, but it's when it stops curving this way and starts curving this way. Like that's the kind of thing you're looking for. So where is it? About right there. So if I did this right, on the left it's up and on the right it's down. I think I got that pretty close. Okay. So I think that's an inflection point. So let's label it. Inflection point. All right, now where's another one? Well, there's another one over here. Similar to the first one, hard to get it in the right spot again. About right there. You did it right. Then on one side it's concave down and the other side is concave up. I think I got that. And it looks like it's concave up all the way, the rest of the way. So we have 2 inflection points. And then what you've got is a section here. This section it's all concave up. The next section, that's concave down. Third section, wrong color. That's going to be concave up again. All right, so again, you're looking at the transition. So like this kind of shape is up, this kind of shape is down. And so right in the middle, that's where an inflection point is, where it switches. And it's not vertical or anything. You could have like, if I do this, like this kind of shape, that's up, concave up, and this kind of shape is concave down. So this is an inflection point as well. This is an inflection point. Okay, so it's not like vertical or horizontal or anything like that. The slope can be whatever the slope is. It's just where it switches from the shape of a concave up thing to the shape of a concave down thing. And those are what those look like. So I'm led to believe that when I'm doing this, if I was trying to mark this the way they said, as long as I got like a vertical line in there and another vertical line in there, or an interval where it's concave down, I think that's all it's looking for. Let me see. It says we don't have to get it perfect. Yeah, that's all they want. So, like those blue lines is basically all they would want when they were saying to mark the place that was concave down. Hey. Concave down. All right. So, so you have some stuff like that that's related to concavity. Give you another one. They make you list out intervals for it as well. Give you a function like this. They say select all the intervals over which the graph is concave up. And what do they mark here? Okay. I'll try to do this the way that they do it. Okay, good enough. And then, so this is the y-axis, and this is the x-axis, and this is at -1, and this is at +1, and yeah, there we go. And so they say, where is graph concave up? And then they give me choices. -infinity to -1, -1 to +1, and 1 to infinity, and then none, and we have to check all of them, like any of them that is concave up. All right, so kind of just let's kind of just highlight the sections here. So -infinity to -1 is this section of the graph. And then -1 to 1 is from here to here, this section of the graph. And then 1 to infinity is this section of the graph. And so let's think about it. Which one is it concave up? So let's just label them. So in the first one, the yellow section, is it concave down or up? Right? Remember what they look like. That looks down, right? So this is down. So not that one. What about -1 to 1? It actually, -1 to 1 starts concave down, and then it ends concave up. So this is actually down, and up. Okay, that's weird, right? It's kind of subtle, but it is, right? Because I know at -1 it's definitely down. So it starts out going down. And I know at 1 it's definitely concave up. So it must switch somewhere in there. And then from 1 to infinity, what is it? That looks up. All right. So where's the graph? Select all the intervals over which the graph is concave up. I guess I would just have to say 1 to infinity, and that's the only one that's on this list. Hold on. Whoa, hold on. I think they did this wrong. They did. They did. Okay. Um, that's a mistake. Yeah, that's definitely a mistake. Oops. I'm going to type this in. This is going to take a second here. Sorry. But I want to get them to fix it. One section is called concave up and is actually concave down. Submit. Fix your stuff, Newton people. All right. Yeah. So interesting. Yeah, they called this so they called this interval up, but that's definitely not up. That's definitely down. So they messed up. Joke's on them. Concave up. Okay, they got it right there. They got it right there. Okay, yeah. So this other one, the next question they got actually right. So they do know what concave up and concave down is. So that's good for them, I guess. All right, one last question, and then I think we'll be done because we're like an hour in. So here's the question for you and for me. R of x, -8x cubed minus 7x squared plus 2x plus 3. And they just say, is R of x concave up or down? At the point, where x equals -2. All right, so again, remember, how do you test concavity? It's just the second derivative. So the steps are very simple here. You're going to find, I was going to say f double prime, but in this case, r double prime. Step 2, plug in -2 to see if it's plus or minus. Positive or negative. That's it. Also, we're going to do this, but we could cheat. Let's cheat first. Oh, well, honestly, that's going to be harder. I was going to say we could just cheat. We can cheat, but hold on. Can I do 2 things at once? Whoa, I can. That's my mail. Don't read my mail. All right. Here's what we're going to do. We are going to just graph this real quick, and I just want to see if we can do it by graphing. So -8x cubed minus 7x squared plus 2x plus 3. There it is. And they say x coordinate -2. All right, so where's x equals -2? All right, well, -2 is to the left of this point. I'm going to change this a little bit. So let's, on my y-axis, let's go to 100. Done. Okay. So think about this. At this point, projector mode. Concave up or down over here? That's concave up, right? I mean, and it changes. Like I can keep going here. Okay, here's 2. Is it concave up or down here? It's definitely concave up, right? Concave up, concave down. So that's concave up. All right, so I already know the answer. It's concave up. Okay, but you can do it with pure math without looking at the graph, or you could do it with the graph. Either or. All right, so let's find r prime. So derivative, that's going to be -24x squared minus 14x plus 2. All right. Double prime, -48x minus 14. All right. R double prime of -2. That is -48, -2 minus 14. That is 96 minus 14. That is 82, which is positive. What's that mean? It means concave up. That's it. Okay, so both of those were pretty fast. I mean, you can graph it and get an answer pretty quick, but you could also take 2 derivatives and plug in the point and get the answer pretty quick. So, you know, what do you want to do? Both are pretty fine. Okay, so I think that's it. I hope that's it. So that's concavity and the second derivative test. And I hope you take away from this that you can do the second derivative test, but you know, sometimes it's not worthwhile. So maybe just do the first derivative test. And that's it. So that's it for now. See you next time. Stop recording.